Hey guys, we're going to do a lesson today over inverse functions. And the first thing you should understand is a relation is a set of ordered pairs. A function is a relation where none of the x's repeat. And you've learned about that since Algebra 1, or and probably even before that. But like when you've been given a set of ordered pairs, none of your x's repeat, that makes it a function. Well, an inverse function, it takes the ordered pairs or that you have in a function and it switches them. So the y's become the x's and the x's become the y's on the new function, on the inverse function. So if you've got any y's that repeat in your original function, they will become the x's on the inverse function, and it won't, it matters if the y's repeat or not, because if they repeat, then the x's will be repeating on the inverse function. And that's what we call a one-to-one function, whenever the x's and the y's don't repeat. That way, both the original function and the inverse will be functions. So in this example, 1 down here, this is a function because none of the x's repeat. But it's also one-to-one because none of the y's repeat. So it makes it a one-to-one function, which means that the inverse will also be a function. In the next example, this is not a one-to-one function because this y right here repeats. If you were to write these ordered pairs, it'd be 1, 4, and then 2, 4. And so those, and then also 3, 6. But those y's right there are repeating. Those y's will become the x's on the inverse function, because when you do the inverse, you'll have the ordered pair 4, 1, 4, 2, and 6, 3. And then your x's are repeating, so the inverse won't be a function. So we say the original function is not one-to-one because the inverse won't be a function. On the next example, it's not a function to begin with, and that's because this x right here at 1 repeats. You've got the ordered pair 1, 4, and 1, 5, and so your x's are repeating there. So that's what we mean by one-to-one. Basically, on the original function, no x's can repeat. That makes the original a function. But then also no y's can repeat because that makes the inverse a function. One way we can check to see if a function is one-to-one is using the horizontal line test. So like if you have the graph of a quadratic, like y equals x squared, it looks like this. It's a U-shape. Well, it is going to fail the one-to-one test because when you do the horizontal line test, it has y's that repeat right there. It crosses that function in 2 different places, so that means that y's are repeating. So when you do the inverse of this, y equals x squared, the inverse won't be a function. So that's just a way to check to see if a function's one-to-one or not. If we did something like the graph of y equals x cubed, that looks like this. And it is one-to-one because when you do your horizontal line test, it only touches that one time. So it would be one. That means your inverse will be a function. All right, down here, properties of inverse functions. There will be graphs of inverse functions or reflections on the line y equals x. So in this picture right here, this is the line y equals x. And you should see that you have a mirror image on either side of that. Given a function f of x, the notation for the inverse function is f negative 1 of x. That's how we show that it's the inverse function, is adding that exponent looking thing that says negative 1. The domain of a function is equal to the range of the inverse, and the range of the function is equal to the domain of the inverse. So just like your x's and your y's flip, when you do an inverse function, you switch your x's and y's. You also switch your domain and range. They flip as well. All right, on this page, they're asking me to graph the inverse function. For each of the functions below, they want me to draw the line y equals x, which in this case, I'm just going to draw it in highlighter. This is the line y equals x. And then what we're going to do is go ahead and take these. Oh, I didn't mean to do that, sorry. Let me draw that again. Okay, so then what we're going to do is we're going to take ordered pairs that we have. For instance, we've got the ordered pair right here at negative 3, negative 2. Well, that will become the ordered pair negative 2, negative 3. So I'm going to go ahead and graph that. The ordered ordered pair -2, -3 is going to go right here. All right, then you've also got the ordered pair right here at 1, 0. And that will become the ordered pair 0, 1. So it'll graph it right here. Let's see. Oh, I guess I missed one that we had. We had the point -2, -1. And that will become the ordered pair -1, -2. So it'll be right here. So your inverse, so let's try to get one more. We've got this point right here at 6, 1. So the ordered pair 6, 1 will become the ordered pair 1, 6. So if I graph that, it'll be up here. All right, so this will look like this. And that's in the red is the inverse function. So if this is my y here, this will be my y to the -1, showing that it's the inverse. Where those two should cross, if they are going to cross, should be on the line right here, y = x. That's where they should intersect, if they're going to intersect. But you should see that it's a mirror image on either side of this line, y = x. All right, on the next one, and this one was a 1-to-1 function. If I would have done the horizontal line test, it would have, only touched it in one spot each time. So that was definitely 1-to-1. All right, on the next one, let's see, we've got this ordered pair. Well, first of all, let me graph the line y = x. I'm just going to draw it like a dotted line. Okay, so then we've got this point right here at -2, 0, -2, so it will become the ordered pair -2, 0. We have the point at 1, -1, so it'll become the point 1, -1, 1. We also have a point at -1, -1, which is also at -1, -1. We have a point at 2, 2, so this point will stay the same. You have a point at -2, 2, so that'll become at 2, -2. So you should kind of see that we have, I keep messing this up, sorry. You should see that you have this right here. All right, well, hopefully you notice that my original function was not 1-to-1. I had y's that repeat. Well, then whenever it became, when I did the inverse function, it was no longer a function, and that's because it had x's that were repeating. So this original function was not 1-to-1, meaning your new inverse function is not a function. All right. All right, algebraically, the way we find that that two functions are inverses of each other is by doing a composition, plugging the one function into the x of the other function. And if you get a result of x, when you do that, then you know that they're inverses of each other. So that's how we show it algebraically. So this next example is asking me to show that each function is the inverse of the other. So we need to do f of g of x. So that means I'm plugging in this g function right here into the x on the f function. So that will be 4 times x minus 3 over 4 plus 3. When I multiply this out, the 4's will cancel, and I'm left with x minus 3 plus 3. And then the -3 and the 3 cancel, and so I'm left with x. Well, I have to do it both ways. So I'm going to do it the other way as well. I'm going to do g of f of x, and I get this time I'm going to be plugging in this into the x on the g function, and so that's going to be 4x plus 3 minus 3 over 4. So that gives me 4x, because those 3's cancel, over 4, which simplifies to be x. So since both of those end up with x to be x whenever you plug one into the other, and you have done it both ways, you know that those are inverses of each other. All right, next we have finding the equation of the inverse. So when you've been given the formula for a function, You want to determine if the inverse is going to exist by determining if it's 1 to 1. Ask yourself, is it necessary to restrict the domain to get the 1 to 1 version of f? So the first step you're going to do is interchange your x and y in the formula, solve it for y once you switch those, and then label it with this f negative 1x, and then state the restrictions on the domain, and then replace your f negative 1 in the new equation. All right, so for each of the following, we're going to sketch the line y equals x, find the inverse, sketch the inverse, and verify that they are inverses algebraically. So I'm going to sketch the line y equals x. All right, then I'm going to find the inverse. Right now, the equation is y equals the square root of x plus 3 minus 2. The reason why my domain has been set for x is greater than or equal to negative 3 is because you've got that function, the square root of x plus 3. You can't take the square root of a negative number. So what's underneath that radical has to be greater than or equal to 0. And so that when I solve that, I get x is greater than or equal to negative 3. So that's why they're saying this right here. You have to let the reader know that x must be greater than or equal to negative 3. All right. Well, I'm trying to erase this, sorry. Okay, so now we're going to switch the x and the y, so that becomes x, and then the square root of y plus 3 minus 2. I'm going to move the 2 over, so now it's x plus 2 equals the square root of y plus 3. I'm going to square everything, so square both sides to get the y out of the radical. Remember, when you square x plus 2, you're multiplying it by itself. And when you square a square root, it undoes the square root. And so when you multiply the left-hand side, you get x squared plus 4x plus 4 equals y plus 3. Subtract your 3, and we get x squared plus 4x plus 1 equals 0. So what you need to make sure you do is, let's think about how we would graph this. When you graph a square root function, y equals the square root of x, it looks like this when you graph it. This point right here, it gets transformed using these. This is in transformation form. So we've gone to the left 3 and down 2. So from 0, 0, I'm going to go to the left 3 and down 2, and here's where my point is. Let's plug in negative 2 into that. So if I do the square root of negative 2 plus 3 minus 2, I get the square root of 1 minus 2, which is going to give me negative 1. So I've got a point right here as well. If I plug in negative 1, I'm going to get something under the radical that I can't take the square root of, so I'm not going to use that. I'm not going to plug in 0, because then I'll just get 3. But now let's plug in 1. If I plug in 1, I get the square root of 1 plus 3 minus 2. That's the square root of 4 minus 2, so 2 minus 2, which is 0. So if I plug in 1, I get 0 for my y value, which is right here. So I can kind of graph that. All right, so that is actually my original function. That's my f of x. Well, now I've got some points I just found. I'm going to write those points real quick. I graph the point negative 3, negative 2. That point will become negative 2, negative 3. I graph the point negative 2, negative 1. Well, that point will become negative 1, negative 2. And then I graph the point 1, 0, and that point will become 0, 1. So I'm going to graph that in a different color. So we've got negative 2, negative 3, which is right here. I've got the point negative 1, negative 2, and I've got the point 0, 1. So this is that graph. This is the inverse graph. So f raised to the negative 1, x. So you should see it's a reflection over that line y equals x. Where those two cross is right there on that line y equals x. So we've found the inverse. We sketched the inverse. Now we need to verify algebraically that they actually are inverses. So I don't know why I set that equal to 0 a while ago. That was a mistake. I'm sorry. Right here, this shouldn't be with 0. It should be y to the negative 1. So, or really, I should say f negative 1 of x is equal to x squared plus 4x plus 1. So if I want to verify algebraically that those are inverses of each other, I'm going to plug in f of negative 1 of x. So I'm plugging the inverse into the original. So that'll be the square root of x squared plus 4x plus 1. I'm plugging that in for x here, plus that 3, all, and then minus 2. So that gives me x squared plus 4x plus 4 minus 2. This factors to be x plus 2 squared minus 2. When I take the square root of something that's squared, it just becomes x plus 2 and then minus that 2. So I get x, which I should. It should equal x. Then if you go the other way, so now I'm going to go f negative 1 of f of x. So now I'm plugging in the f of x equation into the inverse equation. So we'll get that square root of x plus 3 minus 2, that whole thing squared, plus 4 times that, plus 1. So if you square this, you're going to get x plus 3 minus 4 times the square root of x plus 3 plus 4 times the square root of x plus 3 minus 2 plus 1. So this is going to cancel with this. So you'll end up with x, and then all of the rest should cancel out if I've done it correctly. Let's see. This should be a plus 4. Oh, I forgot to distribute this right here. I'm sorry. This should be an 8 plus that one. All right, so anyway, you should get that to cancel out and equal to x right there. All right, let's do the next thing. All right, on the next one, we've got y equals the cube root of x plus 2 minus 1. We're going to reflect this over the line y equals x, so I'm going to go ahead and graph that. Switch my x and y. And then solve it. So move over your 1 first. I'm going to go ahead and cube everything. Cube both sides. So that gives me x plus 1 cubed. When I cube this other, the right side, I just get y plus 2. And then I'm going to go ahead and move over the 2. So subtract it. So we've got y. So I'm going to rewrite this as g negative 1x equals x plus 1 cubed minus 2. All right, so, your graph of y equals the cube, we're taking the cube root of that. So y equals the cube root of x. It looks like this when you graph it. So you've got this inflection point right here that has been shifted to the left 2 and down 1. So to the left 2 and down 1 puts it right here. If I plug in negative 1, I'm going to get an 1 minus 1, which is 0. If I plug in negative 3, I'm going to get negative 2. And so it's going to look something like this when you graph it. All right, on the other one, so we basically had those, well, you had the ordered pairs, negative 3, negative 2, which are going to, the next one will become negative 2, negative 3. You had the ordered pair negative 2, negative 1, which will become the ordered pair negative 1, negative 2. And then you had the ordered pair negative 1, 0, which will become 0, negative 1. So graphing those, we've got -2, -3. We've got -1, -2. And we've got 0, -1. So that's going to look like this when we graph it. So this is the inverse, and this was the original function. And then if we were to plug that in to each other, we would get that they both equal x. All right, let's try something else. Okay, on this next part, this is saying, let C of M be the cost in dollars of M ounces of mangoes. So your C is equal to the cost, and what you're plugging in is the M, the ounces of mangoes. So what do the following statement mean to you? If you 12 mangoes, 12 ounces, 12 ounces of mangoes cost 75 cents is what that's saying. This is saying 8 ounces of mangoes are going to cost 50 cents. Okay, so now we're doing the inverse. So it's the opposite of what we were doing before. So now this is your cost, and this is the ounces. So 48 ounces of mangoes cost $3, and 12 ounces of mangoes cost 75 cents, which we already got from our first example right here as well. It's just different ways to write the same thing. All right, another way to write something similar, we've got suppose W equals P of X is the average daily water in gallons required by a palm tree of height X. So what does this represent? Notice that this is P of X right here. P of X represents, the X part is your height of the palm tree. So you've got a 25-foot palm tree. And so basically what that means is when you do P of 25, you're saying how much water it takes for a 25-foot palm tree, I'm going to say water needed for that 25-foot palm tree. This, on the next one, though, it's doing the inverse. So it's saying 25 gallons of water needed for the tree. All right, on the next one. Well, actually, it's when you have 25 gallons of water, it tells you what the height of the tree would be. Okay, what does the P of V equal 50 tell you about V? A tree V feet tall needs 50 gallons of water. And then rewrite this equation of P of -1. So we would say P -1 of 50 equals V. That would be the way to write the inverse of it. Rather than making this video so long, I'm going to let each of these, you can read these on the answer key on notes, but they're pretty self-explanatory. I don't think we really have much on the homework or really even on the test for this part, so you just might want to look through this on your notes. Okay, so on this next part, we've got the inverse of 4. So what that means is that my y value here for the original function, for just plain old f, my y value is 4, and we're trying to figure out what the x is. So if I go over here to the f function, oh, we made a typo, I forgot. That should be a -4. So we go over here to where -4 is, and the x value is 5. So this answer here is just 5. On the next one, we're going to look and see, for the g function, if this is the inverse, it will be the y value of the original function. So you go over here to the g function when the y is 6 and the x value is 8. So my answer here is 8. On this next one, we need to look and see, first of all, what g of 1 is, and then do f negative 1 of that. So g of 1, go over here, g of 1 is negative 3, and then we're going to do the inverse of f of negative 3. So that means you're going to go over here to where the y value on the f function is negative 3, and that answer is 3 from right here. On the next one, we're going to do g negative 1 of f of 0. F of 0 is right here. Its value is negative 1. And then you're going to do the inverse of negative 1. So that's when the y value on the g function is negative 1, and that answer is 4. So this equals 4. All right, on this next one, it's asking me to find, it says the following rational function is 1 to 1, and wants me to find the inverse. So we're going to take that original function, y equals 2x plus 3 over x plus 2, switch my x and y's, all right, and then what we're going to do is go ahead and multiply both sides by that denominator. That way we can get it out of the fraction. On the right hand side it cancels out. On the left hand side we want to go ahead and distribute that. So this is being multiplied times x, so you distribute that x through there. So that gives me xy plus 2x equals 2y plus 3. I'm going to rewrite that over here. You need your y's on the same side so that you can solve for y. So I'm going to move this 2x over here, and I'm going to move this 2y over here by changing their signs. All right, now then if you'll notice, both of these terms right here, this term and this term, they have a y in common. So we're going to factor that out like a GCF. So y is being multiplied times x minus 2. The reason why we want to do that is because that gets the y by itself, basically. Now I'm going to divide both sides by x minus 2 to get y by itself. And that leaves me with that canceling, and I've got y equals 3 minus 2x over x minus 2. Now this asks me to find the domain. I'm going to find the domain and range of both functions. So for the original function, my domain, all that really matters here is this part right here on the bottom, because that bottom cannot equal 0. You can't divide by 0. So basically we want to know what makes x plus 2. It can't equal 0, so x can't equal negative 2. So my domain for my original function would be negative infinity to negative 2, and then negative 2 to infinity. So what that does is it excludes negative 2. The range is determined by the horizontal asymptote. You can't equal the horizontal asymptote on this. And remember, we did that by looking at the degree of the top and the bottom, and they're the same, so you use your coefficients there. So here, my horizontal asymptote was at y equals 2. So that's what the range cannot equal. So our range will be from negative infinity to positive 2, and then positive 2 to infinity. All right, now for the inverse function, which, by the way, I should have rewritten this as f negative 1x equals that 3 minus 2x over x minus 2. So this is the inverse function here. So the domain for the inverse function will be the range of the original function. So there'll be negative infinity to 2, and then 2 to infinity, which that should make sense because on the inverse function right here, that's what's in the denominator. That's what makes my denominator 0. X minus 2 cannot equal 0, so x cannot equal 2, which is what we're saying with this right here. My range should be the domain of my original. So my range should be negative infinity to negative 2, and then negative 2 to infinity. And if you look over here at your inverse function, you've got this -2 and this -2x and this x. Those are what are going to determine my horizontal asymptote. My horizontal asymptote will be at y equals -2. So that's why that's being excluded on that range right there. All right. Okay, on this next example, if a function is not one-to-one, then its inverse is not going to be a function. So if that's the case, we're going to restrict the domain so that it will be a function. All right, so looking at this is the equation of y equals 2 minus x squared. I'm going to rewrite it as y equals a -x squared plus 2. So any x squared is a quadratic that's a U shape like this. This one has been reflected over the x-axis and it moved up too. So it's right here. If you were to graph it, you would see that it looks like this. Let's see. Down here we have this and this. So it should look something like this. That's what the original function looks like. That's not one-to-one, and the reason why it's not one-to-one is because it fails the horizontal line test. Those y's are going to repeat right there, and those y's will become the x's on the inverse. So what we do to make sure that the inverse will be a function is go ahead and limit the domain to x is greater than or equal to 0, meaning we're just going to look at this side of it. We're going to erase this whole side over here. And so when we do that, that allows the inverse to actually be a function. All right, so we've got this graph right now. What I'm going to do is go ahead and find the inverse. So we're going to switch this, and now it'll be -y squared plus 2. Subtract 2. Divide by -1, so that's a -x plus 2 equals y squared. And then we're going to take the square root. Normally when you take the square root, you have plus or minus. But because we've limited our domain to this right here, and we're not going to do the negative, we're just going to do the positive part of that. So my f -1 of x will be the square root of -x plus 2. All right, if you think about how to graph that, you've got this point at 0, 2. That will now be the point 2, 2, 0. You had a point at 1, 1, so you still have a point at 1, 1. You had, we had a point at 2, -2. So now we've got a point at -2, 2. So it should look like this, going this way. And you should see that that's a reflection over the line y equals x, where those two cross are on that line y equals x. So this is my f -1, and this is my f function. All right. On the next question, it says, suppose f of x and g of x are one-to-one functions. If f of 3 equals 5 and g of 5 equals -2, can you determine if they are inverses of each other? Well, if you've got the point f of 3 equals 5, then it's inverse, so f -1 will have this y value as its x value, and it should have this as its y value. Well, this does not have the same y value of 3. It has a y value of -2. So no, they are not inverses. And that's because x and y was not switched. All right, so that's it for these inverse notes. Thanks. Bye.